Hello, this lecture is on seismic hazard prediction and mechanical characterization using calibrated mind scale and local scale numerical models. My name is Dr. Kathy Kalenchuk. I am the president of RockEng, a Canadian-based consulting firm providing geotechnical services to the global mining industry. I've been with RockEng for over 12 years, and my areas of expertise are focused in underground mining, operational engineering, and ground control. I have particular expertise focused in high-end numerical modeling, as well as seismogenic risk and hazard management. I have prepared this lecture with my colleague, Dr. Neda Dadashzadeh, who will also take the opportunity to introduce herself.
Hello, my name is Neda Dadashzadeh. I am a geomechanics consultant with RockEng. My primary experience is with geotechnical design and analysis with a focus on numerical modeling for geomechanical mine design purposes, design and optimization of ground support, and geotechnical site characterization. I am particularly specialized in advanced numerical modeling for characterization of deep excavation response in brittle rock, including rock burst hazard evaluation and characterization.
We'll begin with the motivation for this lecture. Numerical modeling is a critical tool for managing seismic hazard in underground mines, and this includes the use of global mine scale models as well as local scale drift or stope models. Developing effective strategies to manage seismic hazard in underground mines requires an understanding of the spatial and temporal distribution of mine-wide seismogenic ground reaction. Global mine-scale numerical modeling provides a means to forward predict seismic susceptibility spatially and temporally over the life of a mine, and this facilitates informed decision-making around the development and implementation of both strategic and tactical risk mitigation measures. In order to make forward predictions with reasonable confidence, it's necessary that models be rigorously calibrated to the observed history of seismic activity, and so this lecture will demonstrate calibrating global stress models. At the local scale, numerical simulations can be used to evaluate the underlying mechanisms of rock bursting. This lecture will also demonstrate how comprehensive local modeling processes allow for anticipation of hazardous conditions and improve our understanding of the controlling parameters, which are vital inputs for strategic mine planning and tactical engineering. The outline of this talk will include the following. Model objectives and calibration concepts will be touched on first, and then we will demonstrate calibration process for global mine scale models. When a mine scale model is calibrated, it provides us opportunity to make probabilistic predictions of future seismogenic activity. Calibrated models also enhance our understanding of site-specific conditions. We will also touch on the limitations of global modeling, particularly how to overcome scale effects using multi-scale simulations. And with that, we will lead into mechanistic modeling at the drift or stope scale, prior to summarizing all of the key points. The application of numerical modeling in seismic hazard management can be broadly grouped based on modeling objectives: susceptibility versus mechanistic. Susceptibility modeling investigates the likelihood that a geomechanical system will be exposed to a particular ground reaction. Global mine-scale stress modeling is often a susceptibility modeling exercise. Mechanistic modeling aims to improve the understanding of fundamental mechanics, and this becomes more critical for drift or stope scale analyses. The first half of this lecture will focus on global susceptibility modeling, and the second half will demonstrate drift scale engineering for seismic hazard management. The objective of calibrating a global mine scale model is to understand and identify the stress, strain, and yield state, which are indicative of seismogenic ground reaction. Further to stress, strain, and yield, it is reasonable to post-process parameters and achieve predictions of things such as energy and energy release rates. Model calibration can range from qualitative to quantitative depending on the type and quantity of ground reaction observations and measurements that are available. Seismic data is of substantial value for model calibration. Seismic onset occurs well before peak strength. It generally ramps up in intensity until peak strength is reached, and then it continues post-peak until the residual aseismic state is reached. Because seismic data effectively tracks a rock mass volume as it transitions through the failure process, this allows us to have a basis for model calibration. The first step in model calibration is to develop a ground behavior model, which is the three-dimensional representation of all information for a site that is pertaining to geomechanics. This includes geotechnical data, geological data, domained geological and geotechnical conditions, the as-built and design of excavations, all of the ground performance indicators such as instrumentation data, ground support performance, damage and mechanism mapping, falls of ground records, and boundary conditions including in situ stress and in some cases water. The exercise of data analysis, spatial interpretation, and identification of hazard implications ensures that the practitioners tasked with numerical simulations are more likely to understand or at least conceptualize the mechanics of a problem prior to developing a simulation. This not only helps to streamline the calibration process, but it also facilitates pragmatic results interpretation and meaningful design outcomes. Without a conceptual model of site geomechanics, it can be very difficult to scrutinize the quality of numerical outputs. And so this first step is the most important stage of any modeling exercise, and it is commonly not given the necessary dedication. There are three key points that we would like to highlight. First, knowledge of the geological model and confidence in that model are a must. It's important that geotechnical practitioners understand which regions of a geological model may have low or high confidence in the interpretation of structures, contacts, and lithology distributions. Second, the variability in geotechnical parameterization, which includes laboratory data as well as rock mass classification data, must be quantified, and it is of the utmost importance that the geological controls on geotechnical variability are understood. Lastly, it is necessary to understand how seismic activity manifests as stress-induced excavation damage, and this is really critical to understanding the significance of ground reaction and excavation vulnerability, with consideration for both hazard and risk. Another critical first step is a review of your seismic data, and some key points to consider here are that it is necessary to remove all events from the data set which are not related to the rock mass failure process. For example, crusher noise, ore pass noise, equipment vibrations, etc. A review of the seismic data quality is important, and it is particularly important that source location offsets or poor source location resolution be identified. Poor source location must be corrected where possible through seismic system calibration, and when poorly located events cannot be corrected, they must be removed from the stress model calibration data set. It's important that model stages match our seismic data period, and that model stages be as small as reasonably possible to capture sequenced evolution of stress paths. If necessary, mine development records should be considered. In some cases, sequenced mine development records are not available, and in this case, all the seismicity associated with development advance must be filtered out of the stress model dataset, and calibration is forced to focus on production history only. One approach for comparing measured ground reaction to model ground reaction is by visual inspection of model results relative to seismic data clusters. An example is considered here. We know that the onset of seismicity in a rock mass occurs well before peak strength, and that seismic events continue to occur until an aseismic residual state is achieved. Therefore, seismic events should cluster near the yield front of a well-calibrated model, with events locating within both the numerically predicted pre-peak and post-peak volumes. Visual comparison of numerically predicted yield is only an example. Similar comparisons can be made to stress, strain, or other post-processed outputs. Unfortunately, visual approaches are entirely qualitative and incredibly subjective. Subjective qualitative model calibration severely limits the ability of practitioners to utilize numerical models for forward-looking probabilistic assessment of seismic hazard. To eliminate subjectivity and allow for probabilistic forward prediction, model calibration to seismic data must be statistically quantified. With quantitative model calibration, the numerical model goodness of fit can be statistically evaluated rather than relying on visual correlation of model outputs to the evolution of seismogenic volumes over the historical period of interest. Quantitative model calibration requires the establishment of a criteria of goodness of fit. Fundamentally, we're aiming to define the stress, strain, and yield states which correlate to seismogenic activity. This can be done individually for each geotechnical domain within a model, and the criteria must agree with measured material data. During this process, we must be cognizant of changes in the mechanical behavior due to ground reaction over the life of mine. The mechanical strength and stiffness parameters of a rock mass are relatively unchanged during pre-peak loading, and so it can be assumed that the loading conditions at seismic onset are reasonably constant within the material domain. As cracks propagate and coalesce, the rock mass transitions to a post-peak state, and with the accumulation of plastic strain, material properties take on more substantial constitutive changes than during the pre-peak damage accumulation. Due to this post-peak evolution in mechanical properties, the stress and strain states within post-peak seismogenic volumes can be more difficult to statistically evaluate. It is also worth noting that at the mine scale, with increased extraction ratio, system softening occurs, and this commonly results in evolving strain thresholds over the life of mine simulations. As an example, a stress rate criterion is shown here. This is a widely accepted damage threshold formulation, which relates the major and minor principal stresses to UCS as a linear function. A and B parameters vary depending on mineralogy and rock type. A is typically between 0.3 and 0.5, and B varies from 0.5 to 2.5, but is commonly simplified to 1. Therefore, our differential stress can be correlated to 0.3 to 0.5% times our UCS at seismic onset. The figures on the right of the screen illustrate results considering the stress rate criterion. Stress rate has been sampled at thousands of seismic event locations within an individual geotechnical domain from 2 different models. In these cases, each line represents a different temporal period. However, the same approach could be taken for spatial volumes. Since the loading conditions at seismic onset within an individual domain should be relatively constant, the goodness of fit can be defined by variance in the numerical results. This is easily quantified using simple statistics such as standard deviation. We can see visually that the top plot indicates a better fit than the lower plot because the top plot has lower variability, i.e. scatter, between the different lines. The variability in results can be compared between numerous trials where all the input parameters are systematically varied. The model which returns the lowest variability is typically considered to be the best calibrated. Of course, it is noted that further to stress, strain, and yield states being statistically repeatable within seismogenic volumes, these outputs must also be realistic for each individual domain based on characterization of that respective domain. The parameters and inputs that are varied during model calibration, of course, include material properties. However, we must not overlook boundary conditions, constitutive model, and in some cases, geometry. Using the example criterion provided on the previous slide, a model with low variability, but with the majority of sample differential stress outside of our seismic onset criterion, 0.3 to 0.5 of our UCS, would not be considered well calibrated, and an example of that is shown on the right-hand side of the screen. As I noted previously, most often our calibration processes focus on systematic variation in material properties. However, calibration should not overlook geometry, boundary conditions, and constitutive model. And I'm going to demonstrate some concepts focus specifically on boundary conditions and constitutive model in the following slides. Before I get to that though, a few quick suggestions for improving your goodness of fit. First, focus on narrowing down the inputs that have the most uncertainty. And second, don't stray outside of what can be data justified. For example, if you have to artificially reduce or increase your material strength beyond what is justified by the available site characterization data, there is something wrong with the model, and effort should probably be made to improve your stress state, constitutive model, or geometric representations. I'd like to now demonstrate how boundary conditions are a very important component of model calibration. In numerical modeling, boundary conditions are often or most often related to stress. In some cases, water and thermal loading might be important, but for underground mining, stress is generally the boundaries that we're most concerned about. And when we're developing numerical models, it's necessary to understand the magnitude, gradient, and orientation of our virgin stress state. Virgin stress states in most geological settings are complex due to many factors, including, for example, the weight of our overlying strata, plate tectonics and the geological history of a site, glacial loading, erosional events, etc. This figure illustrates the results of a nice case study that was compiled by Andrew Lariche during his master's studies at Queen's University. The data was taken from a Sudbury area shaft pilot hole, and it clearly demonstrates that the local stress magnitudes, shown by the solid lines in black and in red, have substantial variability across geological boundaries and structures. In this plot, we're looking at depth along the pilot holes on the y-axis and principal stresses on the x-axis. You can see there is a stratigraphic column plotted near the middle of the slide, demonstrating that the sampled data crosses through a fairly complex geological setting. In all geological settings, stress gradients and rotations occur between lithological units and across geological structures due to contrasting stiffness and the natural strain history of a rock mass. Knowledge of the magnitude and gradient, as well as the direction of the virgin in situ stress state, is an essential component of geomechanical studies, and this is often the most data-limited component of our site characterization. So despite the fact that virgin stress states are rarely homogeneous, the most common means to apply stress in a numerical model is to simply initialize global stress states, perhaps with a gradient associated with depth. For in most cases for rock engineering, particularly in complex geological settings, such simplified stress initialization is rarely appropriate when data is available to support model calibration. Advanced global modeling requires that the stress state be initialized in a numerical model through strain-based loading, consistent with the geological history, in order to capture the virgin stress state gradients associated with natural stiffness contrast. So let's look at a case example to demonstrate that stress initialization is a vital component of model calibration. Here we have an underground mine with three dominant geotechnical domains. In the figure on the left, we see mined out shapes in gray excavations, and there's a vertical cross-section cut through the mine, and the different colors are illustrating three different geotechnical domains. I'm not going to read through this table of material properties in detail, but I will point out that domain number 3, shown in green in the hanging wall of this deposit, is particularly less competent than the other two domains. Numerical stress models have been developed for this site using a uniform stress gradient function as well as strain-based stress initialization. Two examples are shown here. The images on the left-hand side of the screen represent the uniform stress initialization using a depth gradient function, and the images on the right-hand side of the screen represent strain-based stress initialization. And you can see that the stiffness contrasts between the different domains contribute to significant stress gradients across those geological boundaries when strain-based stress initialization is applied. This plot is illustrating data that is sampled on a vertical line through the center of our numerical model. The vertical blue line, the x-axis on these plots is showing the ratio between sigma 1 and sigma 3 on the left-hand side and sigma 2 and sigma 3 on the right-hand side, and the y-axis is illustrating depth. The vertical blue line represents the uniform stress gradient function, and all of the other colored lines in yellow, gray, green, and purple are illustrating a number of different models that have strain-based stress initialization. The black dots that we can see in the background represent regional in-situ stress testing data. Now, I'm only going to show you results from two of these models, the one with the uniform depth gradient and one of the models with a strain-based initialization, which happens to be heterogeneous number 4, shown in purple. But I am showing you this figure with all of the additional numerical models to make a point that boundary conditions during model calibration isn't just one or two tests that have to be made. You often have to make several stress initialization tests in order to fully calibrate a numerical model. So let's look at some results. In these models, stress, strain, and yield states have been sampled at thousands of seismic event locations that have been tracked over a 22-month monitoring period. These figures illustrate the pre-peak differential stress within each domain of the stress initialization trials. From these results, we can see two important things. Let's look first at the results on the top row. That's the uniform depth gradient function. We can see that in domain number 1 and domain number 2, the onset of seismogenic activity is occurring well below that 0.3 to 0.5 UCS threshold. When we look at domain number 3, we see a significant amount of scatter in the numerical output, suggesting a poorly calibrated model. Now, if we look at the bottom row of data outputs, this is for this strain-based stress initialization model. First of all, we can see that there is much less variability for all 3 domains, and we've actually improved the fit of domains 2 and domains 3 by forcing those data points closer to that 0.3 to 0.5 threshold. These results are consistent with my experience from numerous mine sites. The geological controls play a critical role in the distribution of virgin stress magnitudes, and so stress initialization processes require iterative testing of domain stiffness parameters and velocity boundaries. The next thing I would like to discuss is the importance of choosing a constitutive model. There are many constitutive models to choose from, and none of them are perfect. I always advise that constitutive modeling should start simple, and complexity should only be added as required where models are performing poorly. When we are selecting a constitutive model, some critical questions should be asked by practitioners. For example, which components of the constitutive model are most important for the application of interest? Are we more interested in high confinement, shear-based damage, or are we more important at low confinement, brittle, spalling, or bursting mechanisms? Next, what do we know about post-peak parameterization, and how much are the model results influenced by post-peak parameterization? What about anisotropy? Anisotropy is applicable arguably to most rocks that we find on Earth. However, is anisotropy and the data required to characterize anisotropy appropriate for particular modeling applications? What about how structures are represented? Should faults be represented as best fit planes or as continuum volumes? Are all of the faults in a geological setting relevant? Do all faults have the same material properties? Next point to consider are the decisions about all of our model inputs supported by data. And that's probably the most important question that we should be asking ourselves when running numerical simulations. So let's look now at a case example to demonstrate sensitivity to post-peak parameterization and post-peak constitutive behavior. We have a numerical model, and we're going to use the same one as I spoke to about boundary conditions. And we've established already that we've got this nice strain-based stress initialization, which has improved our data goodness of fit. Well, now let's look at the next thing where there's uncertainty, and that's constitutive behavior. I've ran 3 different numerical models. The top row represents a numerical model that's perfectly plastic. The middle row of outputs represents a numerical model with strain weakening post-peak, and the lower row of outputs represents a numerical model with both strain weakening and strain softening. We can see that the numerical results for this particular application are almost identical in all three cases. And this is quite an interesting and important observation, because as we add on constitutive complexity, we lose out in numerical efficiencies. And so constitutive complexity does come at sometimes not insignificant expense. Now, this is an important observation also, the lack of sensitivity to post-peak behavior. And it's quite typical for long-hole stoping operations where backfill is employed and the rock mass is generally restrained from large strain mobilization. These models demonstrate that for a low strain, high confinement scenario, there are not significant gains in numerical output accuracy relative to seismic data and statistical repeatability of the results. The extent of numerically predicted post-peak volumes and the resulting stress redistributions are identical due to limited strain mobilization. For case studies where there is more significant strain mobilization, the post-peak parameterization becomes substantially more important, and our model results can vary much more drastically. The extent of post-peak material change is illustrated here again for that same model, and to visualize the significance of material degradation, the plot on the right-hand side of the screen is showing percent change in material properties from peak being 0% change to full residual being 100% change. The fully post-peak states are achieved in secondary transverse stoping pillar cores and in the stress shadowed area along the north abutment of this particular mining front. These regions are inherently relaxed, and even in the perfectly plastic model, or they are relaxed even in the perfectly plastic model, and so the stress shedding gains provided by weakening and softening behavior are near negligible for this particular case. So without providing any meaningful improvements to the engineering outcomes of the numerical results, the improved constitutive sophistication comes at a computational price, increased effort for parameterization, losses in computational efficiency, and it doesn't necessarily add value to the engineering outcomes. So we're always asking critical questions when we're doing model calibration. And in this particular case, that critical question is, a significant strain accumulation is not being achieved, or the areas with the most strain are stress shadowed. Does the strength loss post-peak make a significant impact on global stress redistributions? Once the model is calibrated to historical seismogenic behavior, forward predictions of seismic potential can be made based on defining stress, strain, and yield state conditions. In order to make forward predictions of seismic susceptibility, domain-specific criteria must be established to identify hazardous regions temporally and spatially. This is achieved by defining domain-specific pre- and post-peak stress and strain thresholds for seismic onset and the eventual achievement of aseismic conditions. Stress, strain, and yield states are the rawest form of numerical output, and from these, other parameters can be defined during post-processing, such as deformation, energy, and work. Here's an example of probabilistic analysis for forward predictions, and this is achieved by looking at event density and stress-strain space. In this case, we can effectively evaluate the statistical distribution of seismic event rate, which allows for probabilistic prediction of likelihood of occurrence that can be defined both spatially and temporally during forward simulations. The relationship between stress and strain in seismic regions is statistically quite clean, provided we are considering all domains individually and there is no mechanistic change. Scaling laws, such as Gutenberg-Richter, work well, and the data density distributions in stress-strain space are consistent regardless of magnitude, provided there is no mechanistic change, and I will demonstrate mechanistic domaining shortly. Further to the value add of confidently making forward predictions, model calibration process provides additional insights to site geotechnical conditions, such as the identification of geological unknowns. I've used a simple example of differential stress criterion to demonstrate how loading conditions should be well constrained at seismic onset within an individual domain. When statistical trends are not clean, this can be a key indicator that geotechnical domaining requires refinement. And when the data set is reviewed in 3D, anomalous loading conditions might be identified. Let's consider the data I've shown here as an example. We've got two distinct data populations being sampled within one geotechnical domain that has been reviewed. And there appears to be an anomalous portion of data. So this is reviewed in 3D space, and it turns out that the numerical results in that anomalous data correlate to a very specific area of this particular mine. What are the next steps here? Well, this should trigger a review of our domaining geologically and geotechnically, and maybe the boundary conditions and material composition needs to be locally updated in our simulation. Another opportunity to utilize model calibration for additional value add is seismic hazard management based on identified seismic mechanism domains. The process of back-analyzing ground reaction through model calibration provides key opportunities to investigate how stress path can influence seismic hazard. And in some cases, spatial and temporal regions of a single material domain can be exposed to variable stress path loading, which results in a potential for mechanistic change in our seismogenic ground reaction. As we can see on the slide shown here, there are two distinct data populations that have been sampled within one geotechnical domain of a particular mining area. In stress strain space, we see the yellow data points and the blue data points showing two distinct clusters. The gray points are transitional. When we look at that in 3D space, we can see that the yellow is plotting around the mining front abutments, and in this case, all of those blue points are plotting in the hanging wall footwall. And recall that this is all one geotechnical domain, so same material properties, same geological conditions. When we dig a bit further into the seismic source mechanisms, we can actually see that the areas around the mining front abutment have potential for more intense energy release for generating larger seismic events. And the areas in the hanging wall footwall in this particular case are generating lower energy seismic events. And that's completely related to stress path within similar geotechnical conditions. So in the absence of model calibration, it's virtually impossible to forward predict seismic mode domains for rock burst hazard evaluation. The last point I'd like to make before handing off to Dr. Dadashzadeh is that scale effects are difficult to capture when evaluating problems at the global scale. It is virtually impossible in any practical application of numerical methods to capture inner shell ground reaction within a global mine scale model. And this is largely due to computational efficiencies and long run times imposed by high resolution local analyses within a global mine scale simulation. So local or drift scale mechanistic modeling, in the absence of mine scale modeling, can be severely inhibited because we don't have a global understanding of the geological controls on boundary conditions and material properties, or material behaviors not being accounted for, or the influence of those boundary conditions. So now I'll hand the remaining portion of this lecture over to Dr. Dadashzadeh in order to present local mechanistic analyses.
Thank you, Dr. Kalenchuk. So for the rest of this lecture, I'm going to present a case study where a large magnitude rock burst occurred in the floor of a mine drift. Subsequent to the occurrence of this burst event, distress blasting of the floor has been implemented in all active development headings as a means to mitigate future floor burst hazard. But this blanketed use of floor distressing presented many operational challenges, so optimized utilization of distressing was necessary. So the purpose of this study was to identify elevated floor burst hazard conditions and develop a hazard map in mine scale to facilitate the strategic hazard mitigation and mine planning, and also identify opportunities to optimize distress blast design itself based on geotechnical ground reaction investigations. So the study included 4 extensive numerical study phases. In the first phase, a mine-scale susceptibility modeling was conducted to identify global contributing factors to induce rock burst hazard. Then in phase 2, a detailed drift scale modeling was conducted to further improve the understanding of hazard triggers and mechanics of the failure process. In phase 3, the drift scale model was further used to conduct a sensitivity study considering the various geometrical and geological conditions of the mine. And then based on the ground reaction outcomes from the sensitivity test, a floor burst hazard ranking tool was developed, and a hazard map on mine plan was developed after. And in the final phase, the drift scale model from phase 2 was further used to assess the impact of floor distressing on ground reaction behavior and investigate the opportunities to optimize the distress blast design. So this presentation will mainly focus on phase 2 and 3 studies, as the process involved with phase 1 study was already covered in detail by Dr. Kalenchuk, and I will just briefly touch on phase 4 study here to demonstrate further applications of mechanistic modeling. So the case study includes a 1 magnitude seismic event that occurred in an advancing incline in a mine complex located at about 2,000 meters below surface, which resulted in approximately 20 tons of material to be displaced from the lower wall and floor. The geological setting in the mining area is quite complex, including multiple dikes and regional faults. So this would make the stress conditions complex, as will be shown in next slides. The major geology units includes metasediments, basalt, and ultramafics, where the event occurred in fairly massive basalt. So at the time of the rock burst, the drive was located sufficiently far from other excavations, so the stress conditions would reasonably be assumed as far-field. So several macro events with more than 0.2 magnitude were experienced leading up to the major floor burst event. From underground inspection of the burst locations, an inclined north-south striking structure appeared to play a role in all the damaging events. This structure was consistent with a known joint set family at the mine and was locally identified as a secondary shear or a high persistent joint. Detailed seismic data analysis also identified the similar failure planes as shown in the top figure. This feature was also apparent to be coincident with the general shape of observed heaped material on site. So first phase of the analysis included a mine scale numerical model in FLAC 3D, which was calibrated using mine-wide seismic data and ground reaction observations. Strain-based stress initialization methods were used to reproduce the complex pre-mining in situ stress state. During this calibration process, advances were made in the understanding of the far-field loading conditions and the geological controls contributing to elevated seismic hazard. So it was understood that the local variations in stress tensor were influenced by geological contacts and structures, as you see the stress heterogeneity in this example figure. This white star on the figure shows the location of the burst event, and it was understood from this modeling exercise that the basalt unit locally acted as a stress concentrator relative to the softer and less competent ultramafic and sediment domains. So the complex virgin stress state at the burst location was sampled from the calibrated mine scale model to provide boundary condition inputs for the tunnel scale back analysis of the floor burst event. So in next phase, a drift scale FLAC 3D model was built. The observed structure at the location of the floor burst was modeled as a discrete contact interface. The structure is subparallel to the drift alignment and locally intersects the floor, as is shown in the figure. The sequential excavation and support installation were incorporated based on the actual drift advancement rates. So it was recognized that the ground support simulation would have inherent limitations, but the scope here was to focus on relative ground behavior along the drive rather than specific ground support interactions and outputs like loads or displacements. This slide shows a brief review of the constitutive model that was used in the mechanistic model. So from literature, we know that the shear-based approaches of modeling rock mass failure are unsuccessful in replicating the brittle failure mechanism around deep excavations, whereas the methods which employ the concept of cohesion loss and friction mobilization were shown to best capture the brittle rock damage process. These methods are based on the observations that the cohesional and frictional strength components in hard rocks do not mobilize simultaneously, where in lower confinements, the cohesional strength is the dominant component, while frictional strength only mobilizes at higher confinements. So the in situ rock strength would be an S-shaped composite envelope that extends between the lower bound damage initiation limit in lower confinements to the upper bound spalling limit in higher confinements. In this study, the strain-dependent cohesion weakening friction strengthening model was used. And to calibrate the numerical inputs and the rate at which strength components mobilize, the various excavation damage zone depths were considered to be calibrated against depths identified from literature in similar ground conditions, as well as the depth of damage that was observed in the field at the proximity of the structure. This slide summarizes the 3 excavation damage zones in brittle rock and how they can be identified numerically, which I'm going to briefly review them here as the concepts are relevant for this study. So the inner shell or the highly damaged zone at the excavation boundary includes macro damage where rock is completely failed and cannot further retain load. As the distance from the excavation increases, the intensity of damage decreases due to the local confining pressure. The most extent of damage, which would be the yielded zones in numerical models, is the outer shell, which in reality only includes damage in microscale. So it's important to distinguish between the failed rock in the inner shell and the yielded rock in the outer shell because the mechanical behavior of the rock mass in these zones would be different. The strain burst mechanisms can occur in the transition zone from the inner shell to the outer shell, where the induced stresses would be high. However, the local confinement is not as high as the outer shell to sufficiently isolate the damage. So the rock would be under extension in this zone, and as the induced stresses rise to a critical point when the spalling strength is reached, rock failure would happen. This takes us to the stress path concepts, which will be discussed in detail later. So these plots show the results of major principal stresses at the proximity of the structure in the bottom figure and at a location where the structure is away from the excavation influence zone on top figure. And the plots are taken when the full ground reaction is achieved behind the heading phase. So the model results demonstrated a significant increase in inner shell depth when the structure was exposed, and similarly, the volume of the transition zone at the footwall of the structure was noted to be significantly larger. So investigation of ultimate ground reaction, such as these example plots, allows us to locate the potential burst volume. However, the process of induced stress evolutions before rock failure cannot be captured from these plots. The failure intensity can conceptually be characterized by the study of stress passes as shown schematically in this figure. The failure mechanism in the yielded volume can be violent or non-violent depending on evolution of stress passes from damage initiation to spalling limit. Stress hardening after the onset of damage potentially stores strain energy, which can be released in a violent manner if the spalling threshold is reached specifically at higher confinements. These plots show the stress passes with evolution of major and minor principal stresses by heading advancement at multiple locations at the floor. The top figure shows the massive condition, and the bottom figure shows the stresses at the proximity of the structure. Considerable stress hardening behavior was noted at the foot wall of the structure. Stress hardening was as high as 3 times the virgin major stress at the corners when the structure was encountered, as you see by the black line in the bottom figure, and was in the order of 2 times the virgin major stress at the transition zone, as shown in green. Stress hardening was not as notable in the massive ground condition as you see in the top figures. It was also noted that the stress relaxation and associated potential energy that would release do not occur in massive condition, whereas the structure allowed for significant stress risers to build up at the foot wall within the inner shell and the transition zone, followed by stress relaxation, which would potentially release the stored energy once the ultimate strength was reached. Additionally, the accumulated displacement magnitudes have been monitored at the floor at various locations along the drift. So again, it's recognized that the deformation magnitudes would not be accurate due to limitations of the modeling approach here, but the goal was really to further study ground behavior changes qualitatively when the drift sequence interacted with the structure. So a clear elevation in ground deformations was captured when the structure was encountered by the heading, and the location where the maximum floor displacements were captured numerically agreed well with the shape of the damage and heading location in the field. So from the mechanistic analysis, it was concluded that the stress flow at the floor of the excavation was locally interrupted by the brittle structure, which allowed for elevated stresses at the foot wall. In addition to stress risers developed at the foot wall of the structure, the potential unconfined zone in the hanging wall was also increased, which would act as an energy reservoir for ejection for the burst volume. The local model, such as the example shown here, provides a means to quantify hazard exposure, as the mechanistic analysis can be conducted in different critical scenarios depending on mine plan and geomechanical complexity, such as tunnel orientations, rock mass qualities, and in situ stress conditions. So in order to quantify relative floor burst hazard in mine scale, a set of sensitivity tests were established. We looked into direction of tunnel advancement, principal stress tensor relative to drift alignment. The strike of the structure relative to drift was gradually changed from being parallel to perpendicular to the drive. We looked into various lithologies and also brittleness of the structure, and we looked into various stress state conditions as well. So a set of ground reaction indicators relevant to rock burst mechanism were determined and relatively were quantified so that they would be included in a hazard ranking scheme later. This plot is showing the geometry of the structure with varying orientations along the drive from 0 to 90 degrees. So we defined a hazard ranking based on 6 geomechanical components that would characterize ground reaction in the floor. Some of these parameters were taken from literature and some are metrics directly from the models. As a preliminary estimate of hazard, the parameters were basically multiplied together, but this scheme would need a further validation or calibration process by comparing the resulting hazard maps with actual ground behavior using mine-wide seismic data. This will be addressed further in next slides. The first factor is called the intact stress fracturing, which is from a work done by Professor Dadashzadeh. Using this parameter, it's possible to rank rock types with respect to their dynamic rupture potential based on their brittle character, as represented by the ratio of the uniaxial compressive to tensile strength and the capacity for energy storage represented simply by UCS. Intact stress fracturing is a factor that combines the depth of failing rock in the inner shell with energy storage potential of intact rock, where the depth of highly damaged zone was identified from the sensitivity models within the massive ground. And the influence of the structure on depth of damage was specifically incorporated by B factor, which is based on the depth of inner and outer EDZs at the proximity of the structure, normalized to equivalent depths in massive ground. Factor C includes the stress hardening intensity as a result of this structure, which is a normalized metric based on the maximum induced stresses at the onset of failure. Left figure shows multiple monitoring points along the drive, both at the proximity of the structure and in a location away from its influence, to monitor stress passes in detail to quantify factor C. Factor D identifies failure modes in terms of two behavioral zones in brittle failure mechanism, where spalling-dominated stress fracturing at low confinement and shear rupture-dominated behavior at high confinement takes place. It also looks into how stresses evolve in these zones, specifically in the outer shell problems, in terms of how stress passes would relax relatively, which will be shown in more detail in next slides. The stress state and associated hazard susceptibility was also incorporated through factor E using the well-known criteria based on the far field differential stresses and UCS. And finally, the impact of ubiquitous softening structure was considered in quantifying dynamic failure hazard through factor F, where low GSI reduces burst hazard potential, while brittle failure mechanism would be expected at GSI values more than 65. So from sensitivity tests, each factor was relatively compared for different scenarios. For example, shear rupture mode in all three rock types was captured. However, in softer units, the stress relaxation was observed to start as soon as heading advancement occurs, whereas in basalt, the loads were retained until multiple heading sequences advances and significant deconfinement takes place to induce stress relaxation and potential rock failure process. Finally, a set of tables were developed where each factor was simply ranked based on the results of the sensitivity tests. So this exercise was done so that the hazard ranking could be easily used at the mine for mine planning purposes. A preliminary hazard rating scale has been developed by estimating 4 classes of hazard and associated ranges as you see in the bottom table, and then they were graphically applied to mine development plan, and a preliminary hazard map was established. As I said before, while this study shows the process on how such a hazard map can be established, the tool still would need to be calibrated against actual ground seismic reaction. For example, these preliminary maps need to be compared to ground seismic activity to validate the predicted hazard classes and to calibrate or update the mathematical definition of the hazard ranking if it was found necessary. So to further improve efficiencies and operational engineering, phase 4 was focusing on the stress design optimization by geotechnical investigation of ground behavior. This phase of the study was mainly done by my colleague, Dr. Ali Hashemi, which will be published specifically in future, but I'm going to just give an overview of the study here to demonstrate the further application of the local brittle modeling. So a simplified implicit modeling approach was utilized in this study, where the extent and intensity of blast damage was first determined from empirical and theoretical fundamentals of blast design, considering blast charge specifications and site-specific ground conditions. Once the geometry of the potential blast-induced damage was estimated, the calibrated FLAG 3D model that was developed in phase 2 study was used to study the stresses and ground behaviors by adjusting the rock mass properties and constitutive behavior in the distress zone. So this plot shows the estimation of minimum potential blast-induced damage for two types of blast charges that was determined from Holmberg-Persson criterion and based on the estimation of the minimum PPV threshold that is needed to induce plastic deformations. The critical PPV was determined considering dynamic tensile strength of the rock and the fundamentals from literature. Various design patterns, including the ones prior and after the burst event, as well as the alternative possible options, were tested numerically. Similar to the phase 2 study, stress passes were studied in detail. This plot shows an example of the stress path analysis, where the black line shows the original case at the structure footwall without distressing, and other stress passes show different distress design options, which some of them were successful to effectively mitigate stress hardening. The floor burst hazard ranking process was also investigated with the Destress models to compare relative risk estimation. So because this study was using an implicit approach for modeling of distress blasting, an extensive sensitivity study on the various critical design parameters was conducted, and also to mitigate risk during the application of the study results, a conservative approach was generally implemented to determine blast damage extent as well as potential rock mass softening in distress zone. But as I said, I'm going to skip these details in this talk. So as a conclusion from this study, strategic and tactical seismic hazard management requires global stress modeling to evaluate the spatial and temporal distribution of seismogenic susceptibility. Calibrating with seismic data must establish statistically quantified goodness of fit to make probabilistic predictions of future susceptibility. Calibration is not only about material properties, but the complexities of version stress state is critical, and multiple constitutive models may be trailed. Constitutive complexity is important in some but not all cases. It's expensive when it's done right and must be data justified. Scale effects are best managed by pairing multi-scale simulations where global models establish geological controls, boundary conditions, and mechanistic domains, while local models are required for inertial mechanics. Detailed local scale mechanistic modeling allows for characterization of the rock failure process explicitly. Model calibration is critical to confidently making forward predictions, but the value add goes well beyond predicting the future. It strengthens the understanding of geological controls on seismic ground reaction. It improves geotechnical domaining and also allows for mechanistic domaining. Thank you very much for your attention. Please don't hesitate to reach out if you have any questions or comments through email or our webpage.